quarter has really started to make Couchbase a fantastic product, and I'm really excited to talk about how it fits into the whole NoSQL universe. What we're going to be doing today is going to be going through a high-level overview of some of the patterns in NoSQL, and then we're going to talk about how those patterns are used to solve various NoSQL problems. We'll then go into some of the common characteristics and some of the things we see that are really make NoSQL systems distinct from relational databases, and then we're going to go into a short discussion on selecting the NoSQL systems and getting pilot projects. And then I'm going to turn it over to Dipti, and then she's going to go into some of the things that are very specific to the Couchbase technical architecture. So let's just talk quickly about why this NoSQL movement has become so big. And if you've seen a lot of the sessions, the 3 V's come up quite a bit: volume, velocity, and variability. Things that a single processor relational database management tends not to do very well. And we always like to talk about a 4th one, and that's this whole thing about agility, how quickly your business can respond to changing business requirements. So what we found is that there's been a lot of developments that have really made relational databases not handle all these things, and it's been putting a lot of pressure, and so you're starting to see a lot of cracks in the relational database only IT shops. And just to put this in perspective, many of the big organizations we work with are starting to understand that we're really starting to see evolution from in the 80s and 90s a relational only model, then to the mid 90s where data warehouses have really started to become popular, and now after around 2010, most organizations are starting to really consider the 3rd slice of the pie, which is the NoSQL era, where it's not going to replace the relational databases, it's not going to completely take over data warehousing and your OLAP cubes, but there are a large number of use cases that NoSQL solutions really are designed to scale and handle a lot of new business problems. So let's kind of remember why is this happening, and it's really because of these advancements in distributed databases. When I use the word distributed, I mean that it's not just a single processor with a local memory and a local disk. It's really processors that a large number of shared processors that have started to take over pieces of the database problems, and yet all work together to give a single, elegant, scalable, horizontally scalable, and available system. There's a lot of papers. I think there's 3 of them that I think that are essential reading for people to understand this. The early MapReduce papers that Google published, the big table systems for distributed storage, and then the Amazon DynamoDB papers. All of them have really inspired a whole new generation of architects that don't have the fear of creating new databases. And so what has happened is, starting around 2009, if you look at the number of articles and publications and blogs that had mentioned the term NoSQL, it really started to grow up. And we're starting to see that trend continue. And we think that NoSQL is, even though it's a little bit of an awkward term defining something by which it is not, it is an awkward term, but it is being used in practice. And so people have very specific meanings and connotations when they think of NoSQL. So now let's go in and look at what they're really talking about. What really happened was that people starting to do alternative to relational databases came together, and they started to realize that they couldn't just walk into an IT shop and say, we should use something new. They really needed to have a good set of ideas about why these systems manage business problems better. And it really kind of became kind of a revolution within some large organizations, where they said, we can solve these problems better and faster and cheaper by managing the data using a different set of architectures. So it really became kind of almost a counterculture movement in the database era. So common themes of this in the NoSQL movement, first of all, I mentioned, is horizontal scalability. the idea that as you have more data and more load, more reads and more writes, by adding a single commodity node to a cluster, you can get increased performance. That's very difficult to do with a relational database because as your data gets spread over multiple nodes and you need to do joins between those tables, that data has to flow between those. And so the relational models just tend to have a limit to where they can scale. Another thing we're starting to see is very clever use of two technologies, both hashing and caching. We cover those in our book in pretty much in a lot of detail. We're not going to spend a lot of time in this session, but what we're really talking about is how do you get these queries to get distributed to the right nodes, have them analyze their data and bring it back so users perceive they're using one big database, but it's actually distributed over many nodes. The idea then is to also share resources whenever possible. One of the best examples of that is the mem cache, or the sharing things that are cached in memory on a cluster of nodes. And then the other thing we're starting to see is systems that have very, very simple interfaces whenever possible. If you have a large document, complex structure, you don't actually need a complex API. You can use simple puts and gets and deletes to manage document interfaces and let the database do all the work about handling all the indexing of all those nodes. So common things we'll see over and over again in a lot of these sessions. So the idea then is that when you are confronted with a new business problem in the past, here's your workflow. Does it look like a document? If it does, well, we'll put it in Microsoft Office. If it isn't a document, if it has a more regular structure, we put it in our relational database. The choice was pretty simple, and the choosing task was easy. Now that we have many different options, the process of selecting the right NoSQL database is becoming more complicated. So we're going to now talk a little bit about the 6 major classes of NoSQL databases. And when I say classes, this is sometimes people think of these as patterns, but they're not actually detailed low-level object patterns like you might see in the design patterns books. We call these architectural patterns because they really determine the architecture of your total system. The most important thing about architecture is these are big decisions organizations make. Picking the wrong database architecture can put you in a very, very expensive, hard to maintain system. So picking the right architecture and knowing when the right databases should be used is really the key that we're going to talk about here. I'm going to just cover each of these briefly, but basically the relational and the analytical are what I kind of call the legacy patterns that people have been using relational databases and OLAP cubes to solve. But the NoSQL movement has really made 4 new patterns. The key value stores, column value stores, graph stores, and document stores take their place as a prominent member of the patterns that need to be considered whenever you're looking at a business problem. I think most people are familiar with the relational database patterns, but I just want to make sure a couple things everybody knows is that this pattern, technically called a row store, is wonderful because it is standardized. There's SQL standards out there. People are familiar with, they get trained in them, and there's a lot of good reasons to use them if your infrastructure and training and licenses already support them. They have very mature ACID transactions. They have fine-grained security controls, but they also require. They also have drawbacks. One of the things is you need to do your data modeling up front, and they tend not to scale well over dozens or hundreds of processors. Kind of related to the relational patterns are what we call the analytical or OLAP patterns. These are all based on something called a star schema. A central fact, the central part of the star, which is a long fact table that has one row for every transaction, and then around the edge of the star you have dimensions for time or product or location in retail sales, for example. And what's important about this is they're highly optimized for doing analytical systems and doing pre-aggregated, pre-calculated queries very quickly. And so what we want to make sure you know is that the NoSQL movement isn't trying to replace this pattern. What it's trying to do is look at what it's good at and complement it in a lot of different areas. Because these systems really are designed for yesterday's data, historical data, and they don't support all of the real-time updates that you'd often need in some of the more complex and scalable systems. So the first new pattern that we're seeing in the NoSQL movement is called the key value store. Quickly, we describe a key value store as something that has a small key, usually a string, or for example, you can think of a URL as a web page as a key. And what it does then is stores an opaque value in its database. And when I say opaque, the value is something that you can't do queries on what's inside that value. And the key value stores tend to be very, very scalable, very simple APIs. Amazon S3 is a good example of that. Apache, Amazon DynamoDB. But the problem with these systems is that there's no really easy way to query based on the content of your value. If it's not in the key, it's hard to get the data out. But a lot of the early things on Memcache were based on simple key value stores, and they certainly have their place if you're doing image stores or looking whether a query has already been executed and storing the results of that query based on the hash of your query. So they fit into a lot of other architectures. Another pattern is the column family store. This is where if you think of a spreadsheet that has maybe millions of rows and millions of columns, this is really a good example of extending that key value store pattern so that the key actually has both a column and a row information. These are often called column family stores because the columns are grouped together. But the key is that this is not a relational table. You can't really do queries. You can't say, show me all the columns in the system in an easy way because there could be millions of them. They do have very good scale-out properties, but one of the cons is you really can't query the data inside the blob based on the content of that. And so when you design your rows and columns, those designs are very critical. HBase and Cassandra are examples of column family stores. The next thing we're going to look at is graph stores. Graph stores is when you're storing things that where relational data is, the relationship between your objects really has a prominent value in your overall design. They're really not a matter of pulling all nodes that have a certain property, but actually doing traversals of these graphs. So the friends of the friend problem, social networks, are really ideal for these types of graph stores. Neo4j and Allegro Graph are example of graph stores. And they work very, very well for network-based searches. People use them for geolocation type things. They're very good for finding adding additional information to your queries, such as how many of my friends have also recommended a restaurant or things. But the biggest problem is, just like relational databases need to leverage joins, graph stores tend to not do well if you can't fit the entire graph into RAM. They really also have very specialized query languages, so they may not be appropriate for all general purpose transaction processing. So then we're going to come to the last major pattern, which you call a document store, and Couchbase is an example of early on a key value store, but now has a full document store capabilities. And the nice thing about document stores is that every node in these trees that are stored is something that you could potentially query on. We think of that as not being opaque, but being transparent to your queries. Your logical data can be grouped together, so you don't have to use joins to pull data together. There's no requirements that you store them in rows and columns. And there's no object relational mapping. And one of the things about document stores is they're really ideal for search. We'll talk about that a little bit more. But they also can be complex to implement. They also aren't usually compatible with some of the relational stores unless you're adding additional layers of complexities. But document stores have really become one of the most popular types of NoSQL stores simply because they really have a lot more flexibility, And as the document stores have become more mature, they've also added a lot of the additional features that people need for more industrial strength, enterprise-wide processing. Okay, so that kind of is a good breaking point. Maybe we'll take a stop and see if there's any questions that have come up so far.
This is Baxter. If you have any questions, just type them into the GoToWebinar panel, and then we will take a look at the questions, and Dan can address them. We'll pause here for a minute or two to see if there's any questions that folks have. We have a question. I think this was relating to the graph database example that you gave, Dan, from Mesh, and it says, what is stored in row and columns?
I'm sorry, what is stored in the rows and columns? In a graph store, they don't really have a concept of row and columns. We use the concepts of nodes and the relationship between those. And so in graph stores, those also have properties, so you can do complex queries based on those. But I think you'll find that there is no real similar concept of rows and columns in a graph store, if that makes sense.
Mm-hmm. Oh, I'm sorry. This was not relating to a graph store. This is relating to a columnar database. My apologies.
Oh, okay. So what is actually stored in the cell of a column family store? And the answer is basically any byte array can be stored in a cell. You can store entire images, documents. If you're using a web crawler, you may store the entire content of a web page in each cell, and you might identify it by the row, then might be the URL. And one of the nice things about column family stores is you can also have versions of it in each cell. So you might have a version of what the website looked like last month, and then another version of what it looks like this month with a timestamp associated with that. So that's a good question.
Okay, great, thanks. We have another question about the key value stores. So one of the questions about is it common to use a key value system as a secondary system for things such as caching?
Oh yes. So the answer is absolutely. Key value stores are actually very general structures in computer science, and they can be used in many areas not traditionally associated with permanent, persistent databases. Caches are a good example of that, where your memcache really is a key value store, but it's stored in RAM. So if the computer goes down, you lose everything, and you'll have to reload the cache. But caching is a really good example of using a key value store in memory for very, very fast access. Other systems also extend key value stores to solid-state drives, so you can also have that similar, very fast access, but without that the long read times that you have on disk key value stores. So there's a lot of different ones. There's dozens and dozens of products that start out with key value stores and have different features such as sorted keys add value to that search process.
Okay. Kind of related to that question, there's a question about how the key value store knows where the key value resides over the different nodes.
Yeah, that's a great question. That is really the heart of how do you build distributed databases, is when you have an item, how do you know which node to get the data from, and how do you do that consistently? And the answer for most of the modern system is a technology called consistent hashing, where you take the key and you run it through a hash function that randomly distributes the bits in the first part of that hash. And they'll use those bits as a way to look up a node that data is stored and get the data back. The nice thing about that is that those writes can be done on any node in the network, and as long as they have a consistent mapping of those bits to the node assignments, it'll always go to the right node. Now, if you add another node to your cluster, all you really have to do is change the mapping. So that consistent hashing algorithm is really core to most of the distribution of NoSQL data stores. We certainly cover that in, I think it's chapter 2 of our book on how these systems use consistent hashing.
Okay, great. Thanks, Dan. At this time, I think we should move on, and we'll address more questions later on.
Okay. All right, so I'm going to just kind of quickly go through some of the key areas that NoSQL systems have started. First thing that comes up when you think of NoSQL is large data problems, where you have very high volumes of data, large number of data sets, and because NoSQL systems have this horizontal scalability, people have been using it to solve these big data problems. It's really difficult for people to nail down the definition of what they mean by big data, but in the context of our work, what we try to say is big data is something that just doesn't fit appropriately in your current system, and it's something where you have to kind of think about a new way of solving it and using distributed processing to do that. So we have several examples about that horizontal scalability. The second big area is search. So we'll talk a little bit more about search and why NoSQL systems really do well. And when I talk about search, I'm actually really often referring to full text search, and you might guess that document stores tend to really come out well when you do the precision and retrieval analysis of search systems because they tend to take the entire document information into account. The third area that people are really spending a lot of work on is high availability, where since you have these documents and this consistent hashing algorithm, you can not only assign it to a primary node, but you can also say that there's a backup of a document on another node, and then you can put a third copy on another node. And so distributed processing tends to have much higher availability and much easier to recover from faults of an individual node. The fourth business driver is really this agility we've talked about, ability to quickly adapt to change, where you don't have to do a lot of upfront data modeling. And then the other thing that we'll talk about is this enterprise class thing, where you not only do you need to have security inside your database, not just at the application level, but you also want to be able to monitor anybody who's running reporting tools and secure your data, and then monitoring tools. So those are all things that we look for when people are scaling beyond a pilot project to do multiple systems. So a couple of things are now in common for all these. First of all, this idea of a shared nothing processor, which is the panel on the right side. If you're doing things like in-graph databases where you need a huge amount of RAM, you tend to use this shared RAM model. The shared disk model is interesting because people get the perception that they can use storage area networks to save money. But what happens is if you have a bottleneck of that and you can't quickly have each processor get its data from local disk, you're forcing traffic all out to a local area network, and you almost always have local area network bottlenecks, even if you have gigabit per second networking. So this shared nothing architecture has really been the only one that's been most cost effective across of all platforms except for maybe graph stores. The second thing that we're starting to see in most of these systems is there's two models for storing data on a distributed cluster. Model on the left is we call the master-slave model, where all requests come into a single node, and then there's a distribution mechanism that goes to the actual nodes. And if the biggest problem with that is if the primary node fails, you need to have a secondary node standing by, which is idle when it's not running, when the master is working. So on the right-hand side, we talk about peer-to-peer models, where these requests can come into any node in the network, and the complete information about the entire cluster is stored on every node. So that means that if any node goes down, the rest of them can pick up pretty much without a hitch, and they can rebalance the network, distribute things out. So peer-to-peer models are really the only ones that don't need to have standby nodes that are idle and have been certainly shown to be a lot more effective at having large distributed systems. So one of the other patterns that also comes up is the idea is that with traditional relational databases, you may have a large query that you have to send out to these systems, and they often move a lot of data between the nodes in order to get the query results. With NoSQL systems, one of the things we try to emphasize is that you need to come up with a way that you can send the query to each of the individual nodes, have them each respond with their own results before the data is gathered back. And they frequently do that by accessing their local disk. That means they're not sending a huge amount of data traffic. Maybe some of the results of a query might go across the network. But in general, it's going to give you the perception that you have one large database all working together. Queries really work best if they're doing the queries on the local nodes that have their data. And that's a common theme that's coming up over and over again. So then I'm going to just talk a little bit more about structured search. We talked about how if you have a lot of natural language text, how important it is for you to find documents that contain certain patterns. And one of the contrasting ways of doing this is if you use a straight Apache Lucene, for example, and you're going to take your Word documents or PDF documents, what these tools will do is strip out all the words, maybe do a count of the times that the words occur, but then they don't retain that structure. We call this the flat ocean of words, or the big bag of words associated with every document. The thing about document stores that people are finding is if you retain the structure of the document, that you can do a lot more. If you're doing a search and the keyword that you're looking for is in the title of a document, usually that book is about something, a word in the title. So it should have a much higher ranking when the search results come out. So the structured search really allows document stores to have much better, it's called precision and recall, getting the right documents in the search results, and also making sure that the documents you're not interested in get pushed right down. So if you match something in a bibliography or a sidebar or notes, they're not going to have a higher ranking as if something appears in the title of a document or the chapter title. So structured search is really something that document stores do very well. So then we just talk about a couple other things that I think that are very new to a lot of these systems. Many organizations are using this thing called MapReduce, which is parallel transformation of data. And one of the things that we're starting to see is that as data sets change, people are rerunning their MapReduce transforms over and over again, even though maybe only 0.01% of their data has changed. So one of the things we're starting to look for is people that are keeping the results of prior MapReduce transforms around, and in a sense caching that, and then not having to recount everything, but only having to do an incremental recount with the additional items that have been added. So it's not just MapReduce compatibility, it's also this incremental MapReduce that has become important for people that are adding a few things to a data warehouse. So one of the other things we talk about is agility. That one of the biggest factors that is driving agility in document stores especially is being able to hold the data together, and this idea of shredding. Shredding data is the idea of taking a complex record, like an invoice or a sales item, and chopping it up so that it neatly fits into the rows and columns of tabular structures. But then to get it out, you also need to use these joins. What we're finding is that it's not just the saves, but also the updates. And especially if you put an intermediate layer of objects in, you're actually doing 4 different transformations. You're transforming it maybe from a web page into the objects, from objects into the tabular, from tabular back into objects, and objects back and forth. And there are some powerful tools like Hibernate and Ruby on Rails. But the real question is, why are we doing this? If we can keep our data together in the form of structured objects, we find that it's much easier for our customers to make small changes and not have to change any of these mapping layers. So even though there are big tools that try to handle it, we think it has really become the Vietnam of most application developments, is how do you get things in and out of your object relational mapping layers? Where do you get lost? All these large frameworks of tools, maybe they're not as necessary as people think. If we give people a document store that keeps the data together and still make it queryable if they're building these systems. All right, so where you are on the spectrum of adopting NoSQL really depends a lot on where you've come. People that have been doing OLAP for a while realize that SQL as a query language didn't make it, and so they've adopted this thing called MDX. They kind of made the first step. People that have been trying to store objects in object databases also understand that there's huge benefits, and specifically performance benefits, if you're not having to shred data. People that have come from document stores and graph stores are also starting to see benefits, but what we're really starting to push the NoSQL movement is people that need this Web 2.0 and big data scalability. And it really depends on where you're coming from, of what your perspective are and what your business drivers and what your requirements are. So we want to make sure that you understand that you shouldn't just dive into one option. We want you to really look at your requirements carefully. We want you to go through a checklist of what you really need, and if horizontal scalability, availability, search, object relational, and monitoring are all on your checklist, I think you're going to find that the number of solutions that really meets all those criteria starts to drop down pretty quickly. In our book, we then go through a pretty formal process of looking at the qualities, the illities of the system, and helping you, this is just a sample that we did for a project a while ago, look at how different systems match the requirements. We like to look at it as a glove that matches your hand. If it fits all the different leaves on the tree, then your database is really going to match your business requirements. And these processes help you rank what are your most important requirements, and then go through and see whether or not a database will really meet those requirements. The bottom line it comes down is to architectural trade-offs. You can't always get all the same functions. You can't get compatibility with the old world and yet really go after the new scalable systems. Just like when you buy a car, you can't get a car that has fantastic mileage as well as great acceleration. You need to go through and look at those architectural trade-offs, and then we have a formal process for doing that. So with that, I'm going to turn it over to Dipti, and I'll let her take it away from there. And if there's any other questions right now, we can go through and answer those at this point.
That's great, Dan. There's one question that I think would be great for you to address before we hand it off to Dipti. So a question about security and ACID compliance as it relates to NoSQL databases. Wondering if you could talk a little bit about these NoSQL databases and how it relates to the concept of ACID compliance.
Right. One of the things that relational databases do have is they have very careful control over transaction processing. The term ACID, atomic, isolated, consistent, and durable, are the words for the ACID transactions. And many early NoSQL databases really went for speed and scale out and really didn't consider all the needs of transaction processing. Now what we're starting to see is NoSQL databases, as they've matured, they've put in both the fine-grained security as well as the tools for atomic transactions. And one of the things that you find is because people are storing documents in many systems, they can get all of the same guarantees that they got for row-based transactions, as long as they store some of those things within a document. And maybe Dipti can talk about some of the things in Couchbase that support those things. But I think the key thing is that NoSQL systems now are starting to support a lot more of the most reliable transactions that banking and high-stakes transactions environments need. whenever there's coming up with node or network or database failures, they can guarantee those transactions are distributed not just to one node, but to multiple nodes across not just one rack, but potentially multiple data centers if an entire data center goes down.
That's great. Thanks, Dan. For the folks on the call, we're getting lots of questions. That's really great. We'll try to do our best to address those that come in, but for any questions that we can address, we'll follow up with you afterwards. So don't worry if your question hasn't been answered on the webinar. We'll make sure to get back to you each asker individually afterwards. At this point, let's hand it off to Dipti to talk a little bit more about document databases.
Thanks, Baxter. Hello, everyone. This is Dipti Borkar. I'm the Director of Product Management at Couchbase. And for the next few minutes, I'd like to share a little more technical details about document databases, how the sharding works, how replication works, and so on. So let's jump into the details. Couchbase, just to give you a brief introduction, is a NoSQL document database. And so Dan talked about a lot of different categories of databases, NoSQL databases out there. Couchbase belongs to the document database category, and we actually use JSON, the JSON format, to store documents. So some of you had questions about what kind of format is actually used to store these documents. And different document databases use different models. There are some that use XML. MongoDB, for example, uses BSON, which is a binary JSON. And Couchbase uses JSON, and we compress it when we store it to disk. There's a few key characteristics of Couchbase that really stand out. One is easy scalability. So we use hash partitioning to be able to distribute data uniformly across the entire cluster. And you can grow and scale your cluster without any changes to your application and without any downtime. So your application is actually up and running when you're rebalancing the cluster or when you're resizing the cluster. In addition, we have a built-in object-level cache, which gives users sub-millisecond response times. And this is extremely important for web applications and mobile applications that need a very good user experience. With consistent high throughput, you can scale out to millions of users, and it's a great backend for applications that have a lot of end customers, so a lot of end users, particularly for web apps, whether it's e-commerce or social gaming apps like mobile apps and so on. In addition, the always-on characteristics, for example, online updates, online database upgrades themselves, software, hardware upgrades, mean that you don't really take your database down at all, and your application is always up and running. And then finally, the flexible data model, which Dan talked about a little bit, it's extremely suitable for a large number of objects, or representing a large number of entities. So let's take a look at the differences between the relational model and the document model. In the relational model, as we've seen earlier, data stored in rows and columns. Every row is essentially identical, and either you'll have a value in there or you might have a null value in there. But in a document data model, every document might look very different. It might have different attributes. In fact, there might be documents that belong to a completely different type of object. One could be a customer object, another could be an order object, and so on. But let's take a look at an example of changing one of the main advantages of using a document database, which is schema flexibility. In a relational world, when you change the schema of an application, there are several changes that need to be made. Here we have an example of, let's say, an application that has that's a social application. You have a user table. You might typically have a photo table or a status update table and so on. And if we want to add geo capabilities, for example, to this application, the first thing we probably need to do is create a table. And this is a very simple example. You might have several hundreds of tables that you need to update. But every table needs to be updated. Every row needs to be updated. A lot of these changes might involve downtime, which means application downtime. But the document modeling approach is extremely different. And it gives you the flexibility to make these changes on the fly, because every document looks different and can have different attributes, and so on. So all the information about a specific object or an entity is stored together in a single document. In some cases, if those documents grow very large, then you might separate out some of the entities out of that document. But given that you're storing all this information about a specific entity in a single object or a single document, you don't have to have expensive joins in the back end to aggregate this information. So you can think of it as a pre-computed join in some sense. And so in this example, if we had to update the location of a specific entity, in this case, this is my information here, then we would add attributes to the document itself and extend it further. It can be as complicated as required. It could be a nested JSON object in this case, as you see here with the curly brackets, or it could be a simple attribute that is along with right under the root element. And so as you see, documents in JSON is a very good method for representing hierarchical objects, complex objects, and so on. We'll take a look at some of the examples later on in the presentation. Let's take a look at the architecture, and let's take a look at some of the cluster management capabilities of Couchbase. And I will try to explain how some of the other databases are different and the different techniques that might be used. In Couchbase, every server is identical. Every node looks the same. And so there is no single point of failure. Every node is capable of the same operations. And so it has a data manager part of it and a cluster manager part of it. The cluster manager is responsible for cluster-wide activities like rebalancing of data, redistribution of data, replication, collection of the statistics and metrics across the cluster, and so on. But let's take a look at some of the basic operations as a part of this. So here we have a 3-node cluster, server 1, server 2, and server 3. Every node is identical, as I mentioned, and so every node manages some active data and some replica data. And so the data itself is distributed across all the 3 nodes, and each server manages a subset of it. We use partitions, and so actually each server manages a subset of the partitions that we store across the cluster, and the number of partitions essentially stay the same. But given its hash partitioning, it's extremely efficient, and workload gets distributed uniformly as well, just like the data is distributed. In this case, you see that document 9 is the active version lives on server 1, and the replica lives on server 9. Now, given that we have a built-in object-level cache, and you can run hundreds of thousands of ops per second, even on a single node in the cluster, we have strong consistency within the cluster, which means that for every document, you can only read and write from a single location in the cluster, and that gives you strong consistency within the cluster. Now, next come the application servers and the clients themselves. The clients include a cluster map, and the cluster map has information about all the nodes in the cluster, the partitions in the cluster, and where those partitions live. And so based on this information, they can directly talk to a single server and access the information that lives on the server. And so in this example, document 5 lives on server 1. And so if the app servers and the client want to access, read, write, or update document 5, they can directly send the response over to server 1. Now, this is completely transparent from an application developer. The Couchbase client library takes care of all of this, including topology changes. In fact, let's take a look at how the topology changes would work. In these examples, by the way, I'm using a single replica, but you can have a configurable number of replicas up to 3. What we've seen is with most customers, they have 1 or 2, depending on the size of the cluster, depending on their SLAs, and so on. Now, let's expand this 3-node cluster to a 5-node cluster and see how the data actually moves around. So first thing we do is we add 2 servers with their IP addresses, and all this is through our really nice web UI, admin console. This can also be done over REST API. And once these servers are added, they're not a part of the cluster yet, but they're marked pending. And then we perform the operation that redistributes the data, which we call a rebalance operation, which will uniformly distribute data, both active and replica, across these servers. And so this is happening while there is a live workload running on the server, and there is a switch over for these partitions once a takeover occurs. And at that point, the cluster map gets updated. So once the cluster map gets updated, the client now knows that document 6, for example, lives on server 5 and not on server 3 anymore, and it will continue to access the partitions that are now managed by 4 and 5 accordingly. The replicas, as you see, are uniformly distributed as well, and so none of the servers is essentially overloaded during this operation. Now, what about failover? There were a couple of questions about replication within the cluster, across clusters, and so on. And so let's talk about what happens when bad things happen. And we've seen that with web infrastructures, typically if you're running in the public cloud, for example, or you're using commodity hardware, then servers might go down, and you need to be able to keep up with that using software. And a lot of the NoSQL databases have these capabilities like replication. There's different techniques that are used. We use in-memory replication within the cluster, for example, and so replication is extremely fast because it's from from the memory, from RAM of one node to the RAM of the other node. Now, let's say things are going on as usual. Data is being accessed across the cluster, and server 3 happens to go down. Now, there's a couple of things that an admin can do. We have auto failover capabilities, which will automatically fail over a node and promote the replicas to active, or you can manually fail over the node and then promote the replicas. And so in this case, let's say we use manual failover, the replicas get promoted back to active, and you're back in business. So this process is pretty seamless. And as you can see, the replicas that got promoted were uniformly distributed on all the remaining nodes, which means that no single server is actually taking up a lot more load on the server, because that would just make the server even less healthy. And so this is actually one of the advantages of using hash partitioning as opposed to using range partitioning, which some of the other databases use. Now let's move on to, all right, and then once the replicas get promoted, the cluster map has information about the active partitions and the replica partitions and where they live. And so the client will automatically then talk to the data that has now gotten promoted to active. Now, we released a new version of our software, which is a major release in December, and there's a lot of great features in it. I won't go into all the details in this presentation. We have indexing and querying capabilities that you can use to create secondary indexes, tertiary indexes, and so on, and use Incremental MapReduce for a lightweight real-time analytics on your operational cluster. So obviously, our Couchbase and some of the other databases, NoSQL databases, are meant for operational databases or operational purposes. For analytics, heavyweight analytics, you would probably use another system, whether a more traditional data warehouse or Hadoop or some of the more analytical data management systems. But what I do want to mention is cross data center replication, which is actually quite unique to Couchbase in the way that it's built. So let's take a look at how it works. Now, we've looked at intra-cluster replication and how that works. But let's say you want to grow your application and you want to extend it to another geography. Let's say you want to build a San Francisco data center. We already have one in New York, and we set that up. Now, cross-data center replication is extremely easy. All you do is point one of the servers in one cluster to one of the servers in the other cluster, and that's it. It takes care of the rest. It takes care of finding the topologies. It takes care of finding out which partitions live on which server, and they don't really need to be the same size either. You can have different size clusters, and you can have unidirectional or bidirectional replication, master-slave or active-active replication. There's different topologies. But in this case, let's just keep it simple, and let's say we set up unidirectional replication. Data starts getting moved as it's coming in, as it's written to disk. It will start getting shipped over to the other side based on which partition lives on which server. And in reality, every server would talk to every other server on the remote cluster, depending on where the partitions live and which partition is managing which set of documents, and so on. And so this is unidirectional replication. You can use two unidirectional streams to create bidirectional replication, and this is eventually consistent. So given that the two systems are master-master, and to keep up with the performance of your cluster, we've heavily used asynchronous architectures, both to persist to disk and also to send it out to the remote cluster, which prevents an impact on your front-end load or on your application. And so given the asynchronous replication that we have, cross-cluster replication is eventually consistent, and so data will be different across the two clusters for a period of time, but conflict resolution will pick the same winner across the two systems eventually, and that winner will be the final document that gets stored to both the clusters. So within a cluster, Couchbase is strongly consistent. Some of the other databases are eventually consistent even within a cluster, and so the application needs to handle that aspect a little bit more. Across clusters, Couchbase is eventually consistent, and it supports active-active replication. Just a quick look at our UI. You can see here a large cluster with capabilities to add servers, to fail over, remove servers, and so on. And you can set up XDCR, and we have about 200 metrics that you can actually see live in your cluster, and you can drill down into the node level, into a partition level. So there's several aspects that make Couchbase a great operational database. Now, before closing out, I'd like to talk about a few different use cases where NoSQL databases, and in particular document databases, really shine. Now, NoSQL, as many of you know, it's a new part of the database world. These are emerging technologies. Couchbase, as we try hard to maintain resilience. We have availability and always-on characteristics, but you might have applications that need strong transactionality and extreme encryption and security requirements, in which case perhaps it might still be better to use a relational database, or depending on the kind of data that you're storing, the kind of application, NoSQL might be a better fit. And so some of these use cases will give you an idea of where Couchbase might be a better fit for your applications and where other technologies might be a better fit. So I tend to think of this in terms of a data-driven use cases and performance-driven use cases. As we've seen, document databases are extremely flexible when it comes to the kind of data that's stored in it. And so particularly when you have unlimited data growth or non-homogeneous data, whether it's constantly changing data, sparse data, hierarchical data, a document database becomes a great fit for those kind of applications. I'm particularly seeing a lot of use cases for third-party data or user-defined structures where you might be an aggregator of data, or you might be collecting data from a bunch of different sources. It could be social sources like Twitter, Facebook. It could be other databases that you're managing. It could be other content across your enterprise. And in this case, there isn't really a schema that can apply across all this information, and a document database becomes a great fit. Looking at the performance-driven use cases, especially when you have low latency requirements, high throughput requirements, write high throughput in particular is extremely hard to scale with a relational database. And so for write high throughput, you might want to consider Couchbase, given the included caching tier and the low granularity of locking that we have. If you have a large number of end users, If you have applications where you don't know what the demand might look like, and you might have to scale out extremely fast over a short period of time, you have sudden spikes in data and workloads, you might want to look at NoSQL databases because they're quite good at supporting some of these performance-driven use cases as well. Now, I just want to highlight some of these use cases that we've seen, and we have a large number of clusters that belong to many of these use cases. But I want to highlight a few of them here, given the kind of questions that we're getting. Someone asked, can key value stores be used as a cache or a session store? Absolutely. We have quite a few customers that use Couchbase as a session store, so it's a key value access. These are customers like Concur, which does expense reporting. It's a SaaS application. Sabre, very large travel company that uses it as a session store. In addition, we have high availability caching as another use case. And customers like Orbitz are heavily using it with large Couchbase clusters on top of their e-commerce applications. And so in some cases, you could use part of your application could be driven by NoSQL. For example, you could use it as a high availability cache. But in some cases, your entire application could be driven by, would use a NoSQL database or Couchbase in the backend. It could be e-commerce, it could be a content store, it could be a user profile store that we're seeing quite often. And so these are the kind of use cases which you might think of, which might come up in your environment, and Couchbase or other NoSQL databases might be a great fit for these applications. Some recommended reading. There's Dan's book that's coming up, and you can actually take a peek at it at this website that we have down here. But this would be a great read for just understanding the different options that are available out there, the different kind of technologies that are used, replication technologies, architectural technologies, and based on your application requirements, you probably should look at these options and try to understand what is the best technology, data management technology or NoSQL database, and even the category of database that's the best fit for your application. So with that, I'll open it to some more Q&A, and let me take a look at some of the questions that we have here. A question about points of failures specific to Couchbase. So what are the possible points of failures within the Couchbase architecture? Given that we are a shared nothing architecture, it's every server is really its own, and every node is identical. Let me just jump to every node is identical in the cluster, and so there isn't really a single point of failure. We've availability and consistency are what you'll get with Couchbase. We are strongly consistent within the cluster, and we're highly available using replication. Of course, data is also persisted to disk. So hopefully that answers your question. A question about how to handle large amounts of archived documents. So if an organization needs to leverage the information stored in a large archive of documents, perhaps going back years, does this mean that those documents will need to be reformatted to suit the database? That's a great question. As you look at transitioning from one technology to another, or looking at using NoSQL for some of these use cases, you probably need to think of the data modeling. Data modeling is an extremely important, if not the most important part of this migration process, particularly moving from a relational schema to a document schema. You will need to look at how to remodel these schemas and how to store this information in a document database. Now, if it's stored in XML or some format like that, there might be tools out there, and I think there are tools out there that basically just easily convert XML into JSON first, and then can be stored into a document database like Couchbase or MongoDB. There are some of these databases have limits on the size of the values or the size of the documents that you could store, and so it's more common to store metadata about the documents if they're large documents, PDFs, images, videos, particularly, to store the metadata in a system like Couchbase, and to actually store the media files in a CDN or a media server on the side, because it's actually the metadata that gets heavily hit by users and gets queried by users, and the media itself can be streamed out from another system like a CDN. Couchbase has a 20 MB limit on a document, and so that's essentially the limit for storing large files within Couchbase. Question about data integrity with NoSQL databases. With many of these NoSQL databases, the ACID properties essentially might be different, and as Dan explained initially, there might be different approaches that different databases take. In terms of data integrity within Couchbase, there is only one place to read and write data within a cluster. We persist that data to the cloud to disk, and so it is persisted to disk, and it's durable. In terms of replication and availability, it is replicated to other nodes in the system. And so in terms of data integrity itself, given that there isn't a way of updating the data within a cluster, you have ways of locking, so passive locking, optimistic locking, and pessimistic locking. And so there's different approaches that you could use at the application layer to make sure that your data integrity is preserved. A question about replicas and how they're updated. So how often is the replica updated? The replica within Couchbase is only used in case of failovers or in case of failure scenarios. And so the replica is constantly updated, that means that when a mutation comes into the active server, it will immediately get replicated in memory to the replica node. However, the replica itself does not take any direct application updates, and so it's only used for failover. There are read replica APIs that are available. So in case you're seeing timeouts and availability of data is more important to the application than the consistency of data, then the read replica API can be used to access the replica. But it's actually not recommended, given that most applications might need strong consistency. And there are other databases that need replica reads in order to achieve higher throughput. With Couchbase, actually, you can achieve very high throughputs even with a single server, given the architecture. And so it's not recommended to be used for increasing the throughput. There's probably something else that's going on if you're not seeing a high throughput within the cluster. With that, I think that wraps up most of the questions. We may not have been able to get to some of your questions, but hopefully this presentation has been interesting and useful, and we've been able to answer some of your questions. Do feel free to reach out to us at these addresses, and let me know if you have any questions about Couchbase. Thanks, everyone. Have a great day. Bye-bye.